Today we will discuss about the working principle of centrifugal pump. As you know, centrifugal pump is very important machine used in various industries. It has various applications. So let's understand its working principle. Before going to understand the working principle, let us discuss about configuration of centrifugal pump. Typically, centrifugal pump has two configuration, one impeller and casing arrangement and another impeller, diffuser and casing arrangement. Impeller and casing arrangement used for low pressure application, whereas impeller, diffuser and casing arrangements are used for high pressure applications. So this is a simple configuration of centrifugal pump. So it has impeller, so fluid travels to the impeller and then comes out and it comes to the casing. So if you see the profile of impeller between the blades, you see the area is increasing. So when fluid passing through the impeller, there is a reduction in velocity. Diffusion occurs. Second, if you see the shape of casing is a spiral, so increasing area because the fluid which is coming at this, the fluid is coming all the direction. So if the flow is in this direction, so fluid is adding up. So fluid which is coming here, so all are adding up. So mass of the fluid starts increasing. That is why the shape is a spiral having increasing area to have constant velocity. And secondly, if you see the area is also increasing, casing area is increasing, and that is why there is a reduction in velocity, and so there is increase in the pressure. Same thing can be seen in another way of representation. So this is impeller. It has a hub diameter, it has a tip diameter, this is a blade height. So fluid flows from inlet, travels and then comes out from the impeller and it goes to the spiral casing where there is a reduction in velocity and increase in pressure, and finally it comes out. So this is one arrangement which is impeller and casing. Now we'll see another arrangement which is impeller, diffuser and casing. This arrangement, as I said, is used for the high pressure application. Same arrangement, only diffuser is added after impeller. You can see the shape of diffuser is also increasing. So while passing the high velocity in the diffuser, there is reduction in the velocity and so gain in pressure as per Bernoulli's equation. Same thing you can see here, the fluid flows here and then it goes to diffuser, there is a further reduction in velocity and finally goes to a spiral casing where again further reduction in velocity and gain in pressure, and shape is a spiral as I said to accommodate larger mass to have constant velocity. Now let's understand the working principle of centrifugal pump. Centrifugal pump is having axial inlet and radial outlet. The flow of the fluid is always in axial direction at inlet because there is no inlet guide vane. However, as impeller rotates, the velocity of fluid strikes at impeller inlet at an angle which is called impeller inlet angle. The velocity at which fluid enters at impeller inlet is called inlet relative velocity. As the fluid flows through impeller, relative velocity starts decreasing due to design of larger cross sectional area of impeller. The velocity at which fluid comes out from the impeller is called the outlet relative velocity. The fluid does not exactly follow the outlet blade angle of impeller, but it gets slip in away from outlet blade angle in opposite direction of rotation of impeller, and due to slip head rise is reduced. Typically outlet blade velocity is decreased to approximately 50% of inlet relative velocity. So one thing is very important, there is a slip at outlet of impeller, and because of this head rise is lowered. And second important part is reduction or diffusion of relative velocity is approximately 50%. As per the typically it is for design. Although the fluid comes out from the impeller has a less relative velocity because there is a diffusion or reduction, but due to the higher outlet impeller tip velocity, outlet absolute velocity becomes very high, and which has very high kinetic energy. That high outlet absolute velocity is required to be converted into the pressure, and conversion of high outlet velocity is done in two ways as we discussed based on the configuration. One is casing or another is diffuser and casing. The construction of diffuser is having increasing cross-sectional area, just we have seen this. So velocity decreases and pressure is converted. Casing is designed for a spiral shape having cross-sectional area increasing from start to outlet, and this is done to accommodate increasing mass of fluid to have constant velocity of the fluid. Now Euler head. What is Euler head? Let us understand this. So total energy imparted to the fluid is expressed as diffusion energy head of relative velocity half into V1 square minus V2 square. This is a diffusion of relative velocity energy head. Centrifugal energy head because there is a rotation of the impeller, and because of this energy is imparted, which is expressed as energy head. Centrifugal energy head is half into bracket start u2 square minus u1 square bracket close. Another is a kinetic energy head half into bracket start c2 square minus c1 square bracket close. So total energy head is summation of all three, that is diffusion energy head plus centrifugal energy head plus kinetic energy head. If you add up, half into bracket start v1 square minus v2 square plus half into bracket start u2 square minus u1 square bracket close plus half into bracket start c2 square minus c1 square bracket close. Is unit is joule per kg because velocity in meter per second. So it is a joule per kg. So this is head, but the total energy head is equal to the Euler head, and so it can be written as Euler head is equal to half into v1 square minus v2 square bracket close plus half into u2 square minus u1 square bracket close plus half into bracket start c2 square minus u1 square bracket close is joule per kg, where what are these? v1 v2 u1 u2 and c1 c2 are inlet mean relative velocity, outlet relative velocity, inlet mean impeller tip velocity, outlet impeller tip velocity, inlet mean absolute velocity, and outlet absolute velocity respectively, and all the units are in meter per seconds. At inlet we measure in average or mean diameter, that is why all are mean, and outlet is a outlet. Now let's understand the hydraulic efficiency. If you see this curve, this is x-axis is flow, y-axis is hydraulic efficiency. At design point, at design flow efficiency is a maximum, and off design case, either it is a lesser flow or more flow, efficiency starts decreasing. So hydraulic efficiency is a maximum at design flow. However, if flow is in off design condition, means flow is either lesser or more than design case, then efficiency decreases. Hydraulic efficiency is a consideration of inlet flow losses due to deviation of inlet fluid angle with respect to inlet impeller blade angle. In off design case, the inlet fluid angle does not necessarily strike with the blade angle, and that is why it is always advisable to run the machine at design condition, because if you operate the machine on off design condition, the fluid angle does not match with the inlet angle, and that is why there will be losses. So this is one. Then leakages losses because of vanes, rotating and stationary component, and friction losses while passing through the blades. So consideration, etc., etc. These are called the hydraulic efficiency. So hydraulic efficiency is defined as the ratio of hydraulic head and Euler head. So hydraulic efficiency is a hydraulic head divided by Euler head. So this is hydraulic efficiency. Now, since we know the hydraulic efficiency, then we can calculate hydraulic head and pressure rise. So as per definition of hydraulic efficiency, hydraulic head is written as hydraulic head is equal to Euler head into hydraulic efficiency. Now pressure rise. The pressure rise occurs due to hydraulic head rise. It is hydraulic head or head rise, both are same. It is calculated based on the density of the fluid and hydraulic head. So pressure rise is equal to hydraulic head into density of the fluid. So where pressure rise in Pascal, head rise or head in joule per kg, or density in kg per meter cube. So if you just multiply, it becomes Pascal. Newton per meter square is Pascal. Normally, approximately 50% pressure rise occurs at impeller outlet and 100% pressure rise at casing outlet. So pressure rise is equal to outlet pressure minus inlet pressure, that is pressure rise. So centrifugal pump generates pressure rise, and since you have inlet pressure, just add up, it becomes discharge pressure. This is what it is written here. So pressure measured at casing outlet is the discharge pressure. So discharge pressure is summation of inlet pressure and pressure rise. Because inlet pressure, pressure rise is done by centrifugal pump. So just discharge pressure will be inlet pressure plus pressure rise in Pascal. So this is how centrifugal pump works and produces pressure to the system. The main parts handling the fluid. That is one, impeller. This is the main part for centrifugal pump responsible for energy transfer. And there are three types of impellers available. Closed impeller, impeller having both side covering plate. Semi-open impeller, impeller has one side covering plate and other side open. And in case of centrifugal compressor, this semi-open is also called open type impeller, but in case of centrifugal pump, it has subcategory, so it is called semi-open impeller. And another is open impeller. In centrifugal compressor, there is no as such arrangement open impeller. In centrifugal compressor, we have only closed and open, and in centrifugal it has three. Centrifugal pump, so that is open impeller. Open impeller has a no covering plate, so both side impeller are open, and this type of impeller is used for more viscous fluid. As per the impeller blade profile, it can be classified as a backward impeller. If you see the blades are, this is a rotation of impeller, and this is blade angle, so it is in backward direction. So this is this side and this is rotating in this side. This is a radial direction impeller, and this is a forward because blades are in forward and it is also rotating same direction forward. It is called forward impeller. In industries, normally backward impeller are used. Now diffuser. The function of diffuser is to convert impeller outlet absolute velocity into pressure. The cross-sectional area of diffuser is increasing from inlet to outlet. So the fluid flows through diffuser, velocity decreases, and due to reduction in velocity, pressure is converted as per conservation of energy equation. Now casing, the function of casing is to accommodate increasing mass flow to have constant velocity. The shape of casing is in a spiral, means increasing cross-section area, and it has also function to convert velocity into the pressure. So thank you for watching, and hope you like this video, because the content it has been there is very useful, and really you like this. So thank you for watching.